Welcome to the deep dive. Today we're zeroing in on a really fascinating and honestly fundamental area of maths, trigonometrical identities.
That's right.
We've got a great set of educational materials to work from, and really our goal today is for you to walk away with a solid understanding of what these identities are and maybe more importantly, how they all connect.
Exactly. Think of it like a guided tour. We want to show you the underlying structure, how angles and triangles relate.
Yeah.
We'll pull out those key relationships.
Oh, it's good.
They might look a bit abstract at first, but they're actually built on a pretty solid logical foundation.
Okay, so let's unpack this right from the start. Trigonometry itself. Our sources define it pretty simply, don't they? The science which deals with the measurements of triangles.
Yep, pretty direct.
Yeah.
But the real meat is in the trigonometrical ratios.
Right, the sine, cosine, tangent, and then their partners, cosecant, secant, cotangent, the whole gang.
The whole gang, yeah.
Yeah.
These six are like the building blocks.
Yeah.
And they're all defined by the sides of a right-angled triangle. So if we pick one of the sharp angles, let's call it angle A, in the right triangle, say ABC. Sine A, written sin A, is just the ratio of the side opposite that angle that's the perpendicular. BC to the longest side, the hypotenuse AC.
Got it. Opposite over hypotenuse.
Exactly. Then cosine A, or cos A, is the side next to the angle of the base, AB over the hypotenuse AC.
Adjacent over hypotenuse.
And tangent A, tan A is opposite over adjacent, so BC over AB.
And then the other three just flip those, right? Cosecant A or cosec A flips sine, so it's hypotenuse over opposite AC over BC.
Correct.
Second A flips cosine, hypotenuse over adjacent, AC over AB, and cotangent A, cot A flips tangent. Adjacent over opposite, AB over BC. It's like pairs.
Perfect pairs. And two really key things about these ratios. First, they're just numbers. Real numbers, no units attached, nothing like that.
All right, pure ratios.
Pure ratios. Second, and this is crucial, for any specific angle, like say 30 degrees, the value of sin 30, cos 30, tan 30, it's always the same. Doesn't matter if the triangle is tiny or massive.
Right. Our materials show this with similar triangles, don't they? Like a small one, ABC, and a bigger one, AMN, sharing the same angle A.
Exactly.
Even though the side lengths are different, the ratio BCAC in the small one is the same as MNAN in the big one. That ratio is sin A. The angle dictates the ratio.
Precisely. It's like a unique fingerprint for each angle within that right triangle context.
Okay, so we have these six ratios. Now, you mentioned they're interconnected.
Oh, absolutely. They don't just sit there in isolation. They have these really elegant relationships. We already touched on the reciprocal one.
Yeah, the flipping pairs. Since cosecant is hypotenuse opposite and sine is opposite hypotenuse, well, they naturally multiply to 1, so sin A is 1 over cosec A, and cosec A is 1 over sin A.
And the same logic holds for cosine and secant.
Cosec A is 1 sec A is 1 tan A.
And for tangent and cotangent.
Tan A, 1 cot A over stan tan A. Those feel pretty intuitive once you see the definitions side by side.
They do.
Yeah.
But it gets a bit more interesting. Think about the definitions again. Sine is opposite hypotenuse. Cosine is adjacent to hypotenuse. What happens if you divide sin A by cos A?
Let's see. Opposite hypotenuse divided by adjacent hypotenuse. The hypotenuse is what cancel out, right?
It would.
Leaving. Opposite adjacent. Hey, wait, that's tangent.
Exactly. So tan A isn't just its own thing. It's actually sin A divided by cos A. That's a fundamental connection.
Wow, okay, so it's derived. And if tan A is sin A cos A, then its reciprocal cos A must be, well, the flip of that cos A sin A.
You got it. Those are the quotient relations. They really start to show how tightly woven these ratios are.
Okay, reciprocal relations, quotient relations. What's next?
Next up are the big ones, really, the square relations. And this is where probably the most famous theorem in geometry steps in.
Ah, Pythagoras. A plus B plus C.
That's the one. In our right triangle, ABC, base squared AB pair plus perpendicular squared BCP equals hypotenuse squared AC. Always.
Okay, so how does that link to sine and cosine and all that?
We'll think about sin A plus cos A. Let's write it out using the definitions. That's BCAC plus ADAC.
Right, squaring the ratios.
Which gives you BCAC feet plus ABACT. Since they have the same denominator, we can combine them. BC plus ABAACO.
And BC plus ABE, that is ACI from Pythagoras.
Exactly. So you end up with AC, ACB, which is just
1.
So sin A plus cos A equals 1. Always. This is like the cornerstone identity. It connects sine and cosine directly. It pops up everywhere.
That's really powerful just from Pythagoras. And wait, the materials say you can get more identities just from this one.
You absolutely can. Take that core identity, sin A plus cos A 1. What if we divide every single term by cos A, assuming cos A isn't 0, of course?
Okay, so sin A over cos A plus cos A equals 1 cos A. Sin A over cos A is tan A, so the first term is tan A.
Yep.
Cosec over cosec is just 1.
Right.
And 1 over cosec is sec A, so 1 over cosec must be sec A.
Perfect. So what does the whole equation become?
Tan A plus 1 in the sec A. Or, as it's usually written, 1 plus tan A equals sec A.
Well, see, drive straight from the first one. Now, what if we go back to sin A plus cos A equals 1 and divide everything by sin A instead?
Okay, sin A plus cosine A equals first sin A. First term is 1, cos A over sin A, that's cot A. So the second term is cot A.
Right.
And 1 over sin A is cosec A, so the last term is cosec A.
So put it together.
1 plus cosec A equals cosec A. Amazing.
Amazing.
It's like Pythagoras has these hidden layers you unlock just by dividing.
It really is. And it's super useful to know these in slightly different forms, too, like being able to quickly say sin A equals 1 cos A, or knowing that sec A tan A equals 1. Little algebraic shuffles.
Right. Those rearrangements seem like they'd be handy for simplifying things.
Which brings us right to the main event. Trigonometrical identities. What are they, fundamentally?
Well, the definition seems clear. An equation involving trig ratios of an angle, but the key is that it's true for all values of that angle, as long as the expressions make sense anyway.
Exactly. It's not just true for, say, 30 degrees. It's true for any angle you plug in.
So, does that mean those relationships we just found, the reciprocal ones, the quotient ones, and the 3 square relations are all identities?
You bet they are. They're the fundamental identities. They're the bedrock.
Okay.
And the game, often in trigonometry, is proving that other, maybe more complicated-looking equations are also identities.
Right, like verifying them. How do you usually do that? What are the strategies?
The main approach, and the one you'll use most often, is to pick one side of the equation, usually the side that looks messier or more complex.
Okay, start with the complicated bit.
Yeah. And then you use those fundamental identities we just talked about, substituting, rearranging, simplifying step by logical step, until you transform that side into the expression on the other side.
Like a pathway. You're trying to get from point A, the messy side, to point B, the simpler side.
Exactly like a pathway. Sometimes, though, both sides look pretty involved.
Yeah.
In that case, you might need to work on both sides separately.
Oh.
Simplify the left side down as much as you can. Simplify the right side down as much as you can. And if you can show they both simplify to the same expression, then the original equation must have been true. It must be an identity.
That makes sense. 2 paths leading to the same meeting point. Can we walk through an example?
Definitely. Let's take the first one from our materials. Prove that tan A plus cot A equals sec A cosec A.
Okay. Tan A plus cot A on the left, sec A times cosec A on the right. The left side seems like a good place to start, maybe, because we know tan and cot in terms of sin and cos.
Good instinct. So tan A is sin A cos A. Cot A is cos A sin A. Let's add them. Sin A cos A tan A.
Okay, adding fractions. Need a common denominator. That would be cos A times sin A.
Right, so the first fraction becomes...
You multiply top and bottom by sin A, so sin A, cos A, sin A.
Hold on a second.
Multiply top and bottom by cos A, so cos A, sin A.
Perfect. Now add the numerators.
Sin A plus cos A, sin A.
Uh-huh.
And sin A plus cos A, that's 1.
It is, so the whole left side simplifies down beautifully to 1 cos A sin A.
Okay, we've simplified the left side. Now what about the right side? Sec A, cosec A.
Well, sec A is 1 cos A. Cosec A is A sin A. So their product is...
1 cos A for sin A, which is just 1 cos A sin A. Hey, that's the same thing.
It is. Since the left side simplifies to 1 cos A sin A, and the right side is 1 cos A sin A, we've shown they are equal. The identity is proven.
Nice. Okay, let's try another. How about cos A sin A equals 2 cos A 1? That left side looks interesting. Powers of 4.
It does, but notice it's a difference of squares, isn't it?
Oh, right. X, y, and that fabs into x, y, x plus y.
Exactly. So apply that here.
Okay, so cos sin A times cos A plus sin A.
And what do we know about that second bracket? Cos A x plus sin A.
That's 1 again. Our friend.
Our very good friend. So the whole left side just simplifies down to cos A sin A. Much nicer.
Definitely. Now, the right side of the identity we're trying to prove is 2 cos A 1. It only has cosine in it. Our simplified left side has sine and cosine.
So we need to get rid of the sin A term somehow. Can we substitute it?
Use sin A equals 1 cos A from the main identity.
Let's try it.
Okay, so cos A sin A becomes cos A 1 cos A. Got to be careful with that minus sign.
Absolutely. Distribute it.
Cos A 1 plus cos A. Combine the cos A terms. That's 2 cos A 1. Exactly the right-hand side.
Boom. Proven. See the strategy? Factor, use known identities, substitute, simplify.
Yeah, it's like using tools from a toolbox. Okay, the next one in the list is 1 plus cos A plus 1 cos A, 1 APC, here equals 2 cosec A. Here, maybe expanding the brackets on the left.
It seems like a reasonable first step. Let's see. 1 plus cot egg b is 1 plus 2 cot phase plus coto.
And 1 cut egg is 1 plus 2 cut A plus cote A.
Now add those two expansions together.
Okay, 1 plus 2 cote A plus cote A plus 1 plus cote A. The middle terms, plus 2 cote A and minus 2 cote A, they cancel out.
Convenient.
So we're left with 1 plus cote A plus 1 plus cote A. That's 2 plus 2 cote A.
Can we simplify that further?
Yeah, factor out a 2. So 2 times 1 plus cote.
Oh.
And 1 plus cote is one of our square identities. It equals cosec A.
Exactly. So the left side becomes 2 cosec A.
Which is the right side. Done.
You're getting the hang of this.
It's clicking. How about tan A plus tan A equals sec O. Both sides have powers of 4, too.
Okay, let's look at the left side. Tan A plus tan A. See any common factors?
Yeah, tan A, we can factor that out. So tan A times tan A plus 1.
And what is tan A plus 1?
That's sec A from the identity 1 plus tan A is sec A.
Right, so the left side is now tan A times sec A.
Okay, but the right side is sec A, second A. It's all in terms of second. We still have a tangent term.
Can we replace that tan A using an identity involving second?
Since 1 plus tan A was sec A, then tan A must be sec 1.
Good. Substitute that in.
Okay, so sec 1 times sec A. Now distribute the sec A. That gives sec a sec. Perfect. It matches the right side.
See, it's often about choosing the right identity to make the substitution that gets you closer to the target form.
Okay, this is making sense. Let's try one with fractions. Sin A, 1 plus spec cos A plus thin A, which sin A open pi OXO. 10A is 2 cosec A. Adding fractions again.
Common denominator first.
Yeah, it'll be 1 plus cos A times sin A.
Yeah.
So the first term needs a sin A top and bottom, giving sin A 1 plus cos A sin A.
The second term.
Needs a 1 plus cos A top and bottom. So 1 plus cos A, 1 plus cos A sin A.
Good. Now combine the numerators over that common denominator.
Sin A plus 1 plus cos A is all over 1 plus cos A sin A. Okay, let's expand that. 1 plus cos A in the numerator. That's 1 plus 2 cos A plus cos A.
Right. So the whole numerator is sin A plus 1 plus 2 cos A d plus cos A. See anything familiar?
Yes. Sin A plus cos A again, that's 1. So the numerator is 1 plus 2 cos A, which is 2 plus 2 cos A.
Nice. Can we factor that?
Yep. Factor out a cos.
Yeah.
2, 1 plus cos A. So the fraction is now 2, 1 plus cos A, 1 plus cos A, sin A.
And look at
The 1 plus cos A cancels top and bottom, leaving just 2 sin A.
what is sin A?
Cosec A. So 2 sin A is 2 cosec A, which is the right-hand side. We did it.
Excellent. Now, sometimes the choice of which side to start with isn't obvious. Look at 1 plus cos A, 1 plus AK plus cos A.
Left side looks simpler, maybe. But the right side has cosec and cot, which we know how to write in terms of sin and cos. Maybe start right.
That's what the source suggests, actually. It can be easier. Let's try it. Cosec A is fushis A, cot A is cos A sin A.
So cosec A plus cot A is a first A plus cos A sa. That simplifies inside the bracket to 1 plus cos A, sin A.
Right. Now square that whole fraction.
Okay. 1 plus cos A on top and sin A on the bottom.
Now we want to get to 1 plus cos A. 1 cos A, we have the 1 plus cos A term sort of appearing on top. What about that sin A on the bottom? Can we rewrite it using cosine?
Yes. Sin A equals 1 cos A.
Okay, so the fraction is 1 plus cos A. 1 cos A does the denominator factor.
Another difference of squares, 1 cos A, 1 plus cos A.
Exactly. So now we have 1 plus cos A, 1 cos A, 1 plus cos A.
And one of the 1 plus cos A factors cancels, leaving 1 plus cos A in the numerator and 1 cos A in the denominator. That's it. 1 plus cos A, 1 cos A. We got back to the left side.
Perfect. And the source also notes you could have started with the left side and multiplied top and bottom by 1 plus cos A, a clever trick using the conjugate to get the same result. Multiple paths are common.
That's good to know. Flexibility helps. What about one with different angles, like A and B? Cot A plus tan B, cot B plus tan A equals cot A tan B. That looks tricky.
It looks messy, but the strategy of converting everything to sines and cosines often cleans things up, even with different angles.
Okay, so cot A is cos A sin A, tan B is sin B cos B, cot B is cos B sin B, tan A is sin A cos A. Phew. Substitute all that in.
It involves finding common denominators within the numerator and denominator of that big fraction, then simplifying the complex fraction. It's a bit of algebra, but it does work out. You'll eventually get cos A, sin B, cos B.
Which is cot A times tan B. Okay, so the process works, just needs careful algebra.
Right. The alternative mentioned using reciprocal relations might be quicker if you spot it.
Okay, another one. Cos A, 1 sin A, 1 plus cosec A. Maybe convert cot A first.
Good idea. Cot A is cos A sin A.
So the numerator is cos A, sin A, which is cos A sin A. The whole left side is cos A sin A, 1 sin A. That's cos A sin A, 1 sin A.
Now, can we replace that cos A? We want the right side to have things related to sine.
Cos A equals 1 sin A.
Up that end.
Or 1 sin A, 1 sin A, and 1 sin A, difference of squareds again. 1 sin A, 1 plus sin A.
So the fraction is 1 sin A, 1 plus sin A, 1 sin A.
Cancel the 1 sin A terms, leaves 1 plus sin A, sin A.
And can we split that fraction?
Yeah, into first sin A plus 1, which is cosec A plus 1. That's the right-hand side, just needed rearranging.
Exactly. How about square roots? 1 sin A, 1 plus sin A, cosec A tan A. Square roots often involve multiplying by a conjugate inside the root.
Right, like we saw hinted earlier. Multiply inside the root by 1 sin A, 1 sin A.
Let's try it. That gives 1 sin A, 1 plus sin A, 1 sin A.
The denominator is 1 sin A, which is cos A, so it's 1 sin A, cos A.
Now you can take the square root of the top and bottom separately, assuming cos A is positive in the range we care about.
Okay, so 1 sin A on top and cos A on the bottom. 1 sin A, cos A.
Split the fraction again.
Sin A, cos A, which is sec A, tan A. Got it.
See, multiplying by that conjugate form of 1 was the key step.
Okay, this one looks like a beast. Tan A plus sec A 1, tan A sec A plus 1 equals 1 plus sin A cos A. Where do you even start?
This one has a classic, slightly non-obvious trick. Remember that 1 can be written in terms of sec and tan using a square identity.
1 equals sec A tan A.
Exactly. Try substituting that for the 1 in the numerator only.
Okay, so the numerator is tan A plus sec A tan A.
Now, sec and tan A is a difference of squares. Factor it.
Sec A tan A, sec A plus tan A. So the numerator is tan A plus sec A, sec A plus tan A.
Do you see a common factor in that numerator expression?
Yeah. Tan A plus sec A is the first term, and it's also a factor in the second part. Let's rewrite it as sec A plus tan A. So factor out sec A plus tan A.
What's left inside the brackets?
From the first term, just 1. From the second part, we're left with ek sec A tan A. So 1 sec A tan A.
Simplify that bracket.
1 sec A plus tan A.
So the whole numerator is sec A plus tan A, 1 sec A plus tan A. Now look at the original denominator.
The denominator was tan A sec A plus 1. Hey, that's the same as 1 sec A plus tan A.
It is. So that whole bracket cancels with the denominator.
Leaving just sec A plus tan A. Wow, that cleaned up nicely.
It did. Now convert that to sine and cosine to match the right-hand side.
Sec A is 1 cosos. Tan A is sin A coses. Adding them gives 1 plus sin A plus A, which is the target. That substitution for 1 was clever.
It's a common trick for identities of that specific form. The source also shows you could do it by converting everything to sincos from the start, but it's much more algebra heavy.
Good to know the shortcut. Okay, just a couple more types. Ones where you're given conditions, like if tan A plus sin A is mn A sin A equals n, prove mn 1's 1's 4 and m.
Right. For these, you usually work out both sides of the equation you need to prove separately and show they simplify to the same thing.
So calculate mn money, that's tan A plus sin A, tan A sin A, expand that. It's a difference of squares pattern again, or just expand fully. You get tan A plus 2 tan sin A plus sin A, tan A 2 tan sin plus sin A.
And simplifying that.
The tan A and sin A terms cancel. You're left with 2 tan sin A and negative 2 tan sin A, which is 4 tan sin A and sin A. Okay, so LHS for tan A sin A.
Now work out the right-hand side, 4 hero.
Okay, M is tan A plus sin A, tan A sin A. That's tan A sin A. So we need 4 tan A sin A. This looks different.
Let's try converting tan A inside the square root to sin A cos A. So sin A cos A, sin A.
Find a common denominator inside the root. Sin A cos A, sin A cos A. Factor out sin A in the numerator. Sin A 1 cos A.
And what is 1 cos A?
Sin A. So inside the root is sin A cos A, sin. Is that the same as 4 tan A sin A?
The tan A is sin A cos A. So the right-hand side is 4 sin A cos A. Is that the same as 4 tan A sin A?
Let's see. Tan A is sin A cos A. So 4 tan A sin A is 4 sin A cos A sin A, which is 4 sin A cos A. Yes, they match.
So you have to work both sides down until they meet.
Okay. And the last example type tied in algebra variables, if x is cos b, y is basis eb, and z equals condan A, show x apps plus y bigger bassi 1. Just substitute them in.
Exactly. X sec E becomes a secothes already plus a seco.
Okay. X is b, back as a seco b.
And ZC becomes it is seco C cos E.
So the expression is sec A cos b plus sec A sin b tan A.
See a common factor in the first two terms.
Necessary. Factor it out. Sec A cos b plus sin b tan A.
And cos B plus sin B is?
Doesn't matter that the angle is b, the identity still holds.
Right. So we're left with sec A1 tan A, which is just sec A tan A.
And that's one of our fundamental square identities. It equals 1. Wow. Proven.
It brings together several ideas. So as you can tell, Getting comfortable with these identities means really knowing those fundamental relationships: reciprocal, quotient, square, and getting good at the algebraic manipulation. Practice is key.
Which is why the materials mention exercises 21A and 21B for more practice. Makes sense. And just as a little teaser for maybe next time, the materials briefly mention complementary angles, like sin 90 degrees equals A by A cos.
That's right. Another whole set of useful relationships that show how the ratios for an angle relate to the ratios for its complement. Very handy stuff, but yes, perhaps for another deep dive.
Okay, so wrapping this one up then, we've gone from the basic definitions of the 6 trig ratios.
Sine, cosine, tangent, cosecant, secant, cotangent.
Through the core relationships, connecting them, the flips, reciprocals, the divisions, quotients, and those really crucial square relations that come straight from Pythagoras.
Sin A plus cos A, 1 plus tan A sec cos, 1 plus coto A cosec A, the big three.
And then we saw how these are the tools you use to prove other more complex equations are true for all angles, the trigonometrical identities, using strategies like simplifying one side or both sides, substituting, factoring.
It's really about developing that logical process, recognizing the patterns, and knowing which tool to pull from the toolbox.
Yeah, it's more than just memorizing formulas, isn't it? It's about understanding why they're true and how they fit together. It builds problem-solving skills.
Absolutely. And think about this as a final thought.
Yeah.
All these connections we explore today, they create this incredibly consistent and interconnected system. It's a structure for understanding angles, triangles, and ultimately periodic phenomena all around us. It's quite elegant, really. What other hidden consistencies or unexpected links might you find if you keep digging into mathematics?